Theoretical physics has a strict sequence of operations. Before you can propose the existence of a single particle, field, or force, you have to build the mathematical scaffold that allows it to exist. You cannot simply write down an equation and call it a physical law. You first have to rigorously define the algebraic rules and the topological space where that equation lives. The A framework operates precisely as an architectural blueprint. Today, we are going to examine exclusively its formal mathematical construction. That means we are stripping away the philosophical interpretations. We are setting aside concepts of consciousness, biology, and the ether to look entirely at the pure geometry and algebra underneath. To understand exactly how this model diverges from the standard model of particle physics, we have to reconstruct its universe of equations step by step, starting from its foundational primitives all the way up to its global symmetries. This diagram illustrates the functional space of admissible field configurations, denoted as ADA. Every physical system needs a way to extract measurable data, which we get by pairing the field with its dual space, AD*A, using this exact evaluation map. Physical states do not exist in isolation. They have to interact. In standard gauge theory, we use structures like Lie algebras to govern these interactions. Here, the framework requires distinct binary and ternary operations. The framework introduces a strictly non-commutative binary product, represented by the box times operator. Crucially, this operation is not assumed to be associative, meaning the grouping of interactions changes the structural outcome. For multi-component interactions, it introduces the Nanbu ternary bracket. This handles three body state interactions simultaneously, encoding cyclic antisymmetry directly into the algebra. It also requires a Hopf-like coproduct, delta A. This operator establishes the exact mathematical rules for taking a single system and composing it into multiple interacting subsystems. Because this algebraic bedrock is non-standard and explicitly non-associative, any physical system built on top of it will deviate from the grouping rules found in standard quantum mechanics. Abstract algebra needs a place to happen. We have to localize these algebraic states onto a continuous topological base manifold to define the exact geometry where physical events occur. This surface plot shows how that manifold behaves. Unlike the static background of standard theories, this manifold is active. Its effective metric is continuously rescaled by a dynamic coherence scalar, C of x. To perform calculus on this active shifting surface, we have to construct local charts that map specific patches of the manifold onto measurable mathematical spaces. These charts utilize a specific set of nodal coordinates, and they rely strictly on a quaternonian structure, mapping points using the elements 1, I, j, and k. While quaternonians are associative, they are non-commutative. This ensures that the field carries an intrinsic rotational orientation at every point, fundamentally altering the geometric dynamics permitted within the manifold. This diagram displays the tangent space, TA. We use this to measure instantaneous rates of change. However, the framework warps this space using a weighting function that depends on both coherence and phase entropy, S phi. To track movement along the surface, we apply the Merher-Cartan one-form. This equation wraps around the local frame, encoding the intrinsic rotational curvature of the quaternonian manifold directly into the differential geometry. Taking the exterior derivative of that equation gives us the A vorticity. It expands into a two-form, providing a strict coordinate-free method for integrating these rotational states across the manifold. When you integrate these specific differential forms over a tangent space, weighted by phase entropy, the math forces an unavoidable result. The manifold must contain intrinsic geometric torsion. A static geometric space is useless without a mechanism for change. We need a mathematical operator that can take these states and evolve them forward in time. This diagram illustrates the central dynamical engine of the framework, the Dirac E operator. It expands the standard Dirac equation by adding internal phase space terms that are explicitly coupled to the field's coherence and entropy. The standard Dirac operator only accounts for flat spacetime and particle spin. This version forces the system to evolve according to the internal organization of the field itself. Because this internal geometry is constantly twisting, normal derivatives fail to preserve conservation laws, we have to implement gauge covariant derivatives. These covariant derivatives track how the phase structures change while adjusting for local frame rotations. This ensures that the quaternionic phase structure remains invariant under local SU2-like gauge transformations. By locking these pieces together, the Dirac-Lamier operator successfully unites external spacetime evolution with internal phase space rotation under a single rigorous gauge symmetry. With the geometry, the operators, and the functional pairings defined, we can aggregate them into a single equation, the master action functional. This dictates the total dynamic behavior of the field. But constructing a mathematically rigorous framework is only the first step. Writing the equations is very different from solving them. There is a critical unresolved mathematical hurdle, proving the topological stability of localized coherent structures, which the framework refers to as reality nuts. Standard topological methods fail to prove stability here. While the coordinates are quaternionic, the field-level interaction product is non-associative. This causes traditional stability rules to break, as the grouping of field interactions can lead to divergent results. To prove these knots can actually persist, physicists will likely have to invent entirely new homotopy group methods that map specifically to the three-sphere. If this topological persistence can be proven, it provides the mathematical bridge between abstract field dynamics and organized structures. It explains how specific configurations of the field can resist phase entropy and emerge as stable macroscopic complexity.